Hello and welcome to section 11, Marine Facies and Unconformities. There's a lot to know about this and it's a foundational piece of our course, so let's get started. So I'm going to share a story about why universal geology language is so important. I was flying back from Hawaii on the red-eye flight years ago. And I had just been on field course and organizing my pictures from Hawaii, all of the above. So I had some really great pictures of Zion National Park and Bryce Canyon National Park. And I was sandwiched between two individuals and then someone that spoke a foreign language on the other side. So the foreign language individual was sitting on the aisle seat. I was in the middle, sandwiched between these two gentlemen. And it is way past midnight. Most of the plane's asleep, and I couldn't sleep. I was thinking, I'm just really tired, but I was very uncomfortable. So I'm looking through my pictures on my laptop, and the gentleman next to me went, "Oh!" real excited. And he was speaking in Chinese. And I was like, I don't speak Chinese. I need to talk to this man. And I mean, the plane's starting to wake up and the people around us are like, shh. And so I just kind of look at him like, what's your deal, dude? Like, what's going on? And then he gets out one of those barf bags. And I'm really like, this is getting stranger by the minute here. And then he starts drawing pictures of rocks. He was drawing rock symbols. He was drawing cross-bedding and sandstone, and turns out this guy was a petroleum geologist in China. But we may not have shared the same language that we would have spoken for our native tongue, but we certainly spoke the same universal geology language. That's why rock symbols are important, because they're depicted the same way across the world. And so any kind of map or diagram, rock symbols are uniform. Now, there are literally hundreds and hundreds of rock symbols. The United States Geological Survey has a rock symbol for every subtype of, like every volcanic rock, every igneous, phaneritic rock, every metamorphic rock, every sedimentary rock, special types of like graded bedding, cross bedding, mud cracks, you name it, everything's there. So we're just going to learn a handful because this is an introductory course. And I think it's important for you to be able to interpret maps and not be so overwhelmed with the hundreds and hundreds of symbols that are there. So, my new Chinese friend I made, I was endeared to him forever because we could speak a language together and beat our lack of knowledge of each other's regular language and speak one that we both knew very well. We were fluent in geology. So let's get started and talk about how rock symbols are drawn. We're going to start with conglomerate and breccia. So you remember from sedimentary rocks that Breccia has approximately 50% or more angular clast. Well, conglomerate's just the opposite. It should have more than 50% rounded clast. So if you look at our elementary drawings here, that's all they are, is the basic symbols. You'll notice that the clast in Breccia has a predominance of angular clast. I will never say that you won't see a rounded clast in a breccia. That's probably not true. But there's some you might, but most of them are going to have predominantly angular clast because they likely were mass wasted and got buried very quickly. And this conglomerate, well, those rock clast were carried in a river and bounced around the bottom and got that angular shape morphology all worked off. And that's why we draw rounded clast. Now, it would be incorrect to draw either one of these with just angular or rounded circles or squares or whatever shape you want to without putting some smaller clast in between, because there are smaller clast in each of these rocks. So be sure that you do an assortment of both when you're drawing conglomerate and breccia. All right, so very commonly these three rocks are shown together. I'll explain more in just a little bit about why. Shale, siltstone, and sandstone. And the reason that you see them in block diagrams and on maps regularly for geology is these represent very specific depositional environments, specifically marine facies. So you can certainly form these rocks on land, every single one of them, but when we start learning about marine facies, you'll go, oh, okay, I get it. So shale is super fine grained. If you'll notice here, do you see how these sections right here look like very fine laminate layers? Well, that's why we draw shale with all dashes, because it's supposed to represent the layers of sheets of paper that we see with the really, really tiny microscopic clasts that make up shale. Let me come back to siltstone in the middle, but let me come over here to sandstone for a second. So sandstone is made up of clasts that are 0.0625 millimeters to 2 millimeters in diameter. Typically, most sandstone, not all, is very similar in its grain clast diameter size. For example, this is a quartz sandstone, and so these individual dots should be fairly rounded and they should be small to indicate that you got sand grain sediments. So if you go back to the middle one, siltstone, you'll notice that you got shale and then sandstone. Well, siltstone sits in the middle of the class size between shale and sandstone. That's why we use a dash dot, dash dot, dash dot process, because it has some clay material in it and it's got some sand material in it. So you need to have a combination of both. Make sure that you can draw these, because for testing purposes you may very well be asked to draw these on exam, or be able to recognize a drawing and say, yep, that's what that is. If I saw all dots a similar size, I would know that's sandstone. If I saw all dashes, I would know that's shale. If I saw dash dot, I would know for sure I was looking at siltstone. So another two common rocks are limestone and dolostone. So there is a fundamental difference, as you learned in sedimentary rocks, between the two. While they are both in the family of chemical sedimentary rocks that do have calcite in them, the difference between limestone and dolostone happens to be one major thing. Dolostone has some magnesium in it, so that means it is a little harder than limestone. So when we draw it, we need to make sure that we are using slanted bricks instead of regular bricks. So you might wonder, who decided to make limestone and dolostone have these fancy bricks? Well, in nature, that's what these rocks look like. They actually look like they're bricks stacked one on top of the other. And so it's very direct way that geologists decided to draw these things in the most basic, fundamental way that people everywhere would recognize them. So remember, straight up blocks are going to be your limestone, and tilted blocks are going to be your dolostone. So I mentioned the United States Geological Survey has like dozens and dozens and dozens of different symbols for igneous rocks. And in your book, I didn't really like the way our plutonic rocks showed up, so this is a better look at what they should be like. It's supposed to match a phaneritic texture where you have interlocking crystals. And then, I joke you not, one of the fundamental ways that you can draw volcanic rocks is with V as in volcanic. So here's the deal. I can't even begin to teach you all of the rock symbols for igneous rocks. It would be a whole class in itself. So if you're interested, go check out the USGS rock symbol page and start seeing how we draw granite, and we draw gabbro and andesite that's porphyritic, and how we do obsidian and all these different things that you can find, like bahoyhoid, basalt. So all of these have symbols. So we're just going to make it simple in our class. We're going to say if it has interlocking crystals, it's plutonic. And we're going to use the phaneritic texture, which is this thing right here, to depict what we would see in this matrix of granite right here. This is just a piece of rhyolite. There's nothing fancy about it. It's just a volcanic rock. So you would put V's for volcanic all the way through your box. Not tilted V's, straight up V's. All right, so there are a couple of other rocks that are somewhat common on geology maps and diagrams. So coal is one of them. Well, there are different grades of coal, obviously. There's the lignite, the subbituminous, the bituminous, and the anthracite. So the most common drawn coal is actually bituminous, which is what you're looking at right here. And what happens is, remember, coal forms from shale that has a lot of biological plant decayed material in it called peat, P-E-A-T. And so when it gets compressed and heated, it's going to take that all dashes, that shale, and kind of compress it. That's what you're looking at right here, is that you're just seeing that heat and pressure has been applied to shale that has that biological component. All right. Metamorphic rocks, just like igneous rocks, have dozens and dozens of various different rock symbols. To make it easy for both foliated and non-foliated in this class, we're just going to learn about one and use that for every single metamorphic rock we have. In reality, there should be a differentiation between foliated and non-foliated. You have enough to learn. So we're just going to make one category for now. So you make kind of like lightning bolts that are zigzags all the way across, and that's representing heat and pressure. That's exactly what we're looking at here. All of these rocks will get put onto maps and block diagrams, and that's how my friend that I made on the airplane in Hawaii and I were able to communicate, because he could draw these rocks and I could draw them right back. And between us, we were able to clearly decipher and understand each other's backgrounds. And it didn't take me any time at all to learn what gas station, or not station, but gas company he worked for, oil and gas. And I was like, hey, my sister's an attorney with this company. And he's like, oh, and he was able to share this stuff with me. And it was like really cool. So kind of like math is the universal language between people, so can rock symbols be. All right, that brings us into why did you need to know the rock symbols? We're starting to get into the part of the course where rock symbols matter. So remember I said limestone has a blocky appearance. Here's a great look at that. This is at Lover's Leap, right along the trail that goes from McLennan Community College to Cameron Park in the city of Waco. And this is a block of limestone, and in between it are some shale layers that are called kind of a marl, M-A-R-L. And so what's really important about this is this outcrop right here represents multiple sea level changes. But I did want to point out the big blocks and bricks. That is why we draw limestone the way we do. If I have limestone sitting right in the middle of Waco, Texas, we're a long way from the coast. So that would mean that at some point, specifically in the Cretaceous period, around 80 million years ago, there was a shallow epiric sea. So let me hit that word epiric head on. Epiric simply refers to widespread shallow seas. So this is like one of those fundamental moments in geology that not everyone's probably going to agree with that's a geologist, but we'll use it for this course. So what's shallow and what's deep? That is relative, obviously. To me, the deep end is deep and always will be in a swimming pool. But when I took my first submersible dive and a two-man sub, deep got a completely different paradigm for me. I saw it with a new pair of eyes. Basically, deep refers to something in a place in a marine environment, or even a lake for that matter, where light can no longer penetrate. So the abundance of biological life will reduce substantially. So when you're talking about epiric shallow seas, they could range from anywhere from 700 or 800 feet down to 10 or 15 feet in depth. So how deep was this water? I'm guessing several hundred feet at best, because we have fossils from corals and fossils from all types of marine organisms that lived during this time frame. So I'm going to guess, based on what we know today about coral reefs, that is approximately the depth that would have been here in Waco, Texas. I'm sure there's some literature out there that would state this is what we really think based on hardcore evidence. And if that's the case, that's the depth I would go with. But right now, just giving you the best guess I can, I would say up to several hundred feet or less in depth. So we had that for millions and tens of millions of years in Waco, Texas. And why was it the case? Because we had transgressive seas, which you'll learn about in a minute, that invaded the continent multiple times throughout geologic past. But during dinosaur time frame, we had it for an extended period of time because the Cretaceous interior seaway existed right here. So X marks the GPS location right at this point, and all along the Brazos River where you can hike and boat, you'll see these outcrops, and that is totally what you're looking at, are transgressive and regressive sequences. Marine facey rocks. You're like, oh, I just got the rock symbols down. If you are looking at a coastline and that coastline is being bombarded with waves, then you would know that it would be a pretty intense thing. So I wanted to give you perspective about a shoreline. This is actually Green Sand Beach in South Point, Hawaii. And I realized that a lot of people don't have a reference point for how rigorous that a shoreline can be. So when you're looking at these waves coming in and you see these people here and you see how it can move the sand. So now that you've seen that shoreline video at Hawaii, just a glimpse at what a shoreline could look like, then you could understand how we could make a higher energy beach like this right here. This is the type of rock that could form there. And as you learned in sedimentary rocks, we can determine if that was actually made in a beach environment where there was water, because the grains of quartz get lubricated with that water and they don't become frosted. Where in a Aeolian desert environment, those are smashing together without any lubrication and they become frosted, just like a marble would if you were playing with marbles. All right, so you have to imagine that the siltstone would form further away at the same time as the coastline is making that sandstone. You would have the near shore environment where there's not quite as much energy, but still enough to get the banging up of, let's say, corals or algae corals, or even bedrock in the area that is becoming weathered. Rivers can also bring in detrital material that can mix in, and that's why we can get even some detrital stuff in the siltstones and shales. So as we move further away from the near shore, we get into a quieter depositional environment that's making rock at the very same time that the near shore and the coastline is making sandstone. This lagoonal rock is called shale. Now, I will tell you there are deep water shales. They look different from this. They're also made of generally different material. But when you think about shale, I think about the shale that forms in many coral reef environments that are fairly quiet. And there are some coral reef environments that have quite a bit of currents where they're going to have more sands that are there. But this would be your typical lagoon. Eventually, I'm going to get far enough away from the coastline that even the tiny stuff that makes up shale, the detrital-clast, just can't settle out anymore. So you're going to be making sediments the chemical way for sedimentary rocks. Which brings me into the limestone of marine facies rocks. So you can see this is a fossiliferous limestone. Here's a bivalve fossil. I even see a couple of molds here since you've learned about fossils now. But the deal about limestone is that it has a minimal input of terrigenous sediments. So you've learned about terrigenous all semester. That means derived from land. So let me be clear that in a coral reef environment, a couple of ways that you could get sediments at your coastline. One is via the river deposition from terrigenous weathered sediments. Another would be the waves you saw breaking up the bedrock in that area. So the beach that you saw at Green Sand Beach in Hawaii is breaking up olivine basalt, creating that green beach. There's still a third way. So we can actually break up living material like corals, algae type corals, and then anything that's calcium carbonate based. But believe it or not, there are even fish that poop out sand. And these fish help add sand, but they're really just cleaning it out. They're eating rock material that are calcium carbonate. So there's lots of sources of material that can make the detrital stuff that we see in sandstone, that we see in siltstones and shales. When it comes to limestone, though, we are too far away from that material to make it. So you could have some, but it's going to be far enough away that we have minimal terrigenous input. So it's primarily made from the decay or death or breakdown of calcium carbonate organisms, especially microscopic organisms. So it's the material, the rock material that makes up limestone is just generated a completely different way. That's why it's not considered detrital. Understand that you can form limestone in shallow water. That's something that kind of has bugged me over the years when I hear geologists say, well, you can only form limestone in deep water. What I think they're meaning to say is far away from a coastline, like terrigenous. So I've been in the Bahamas and I've been diving, just hundreds of yards away from a small island, and there was calcium carbonate material that was going to turn into limestone at some point in less than 15 to 20 feet of water. The key was we were far enough away from terrigenous input of any substantial input to make a different rock like sandstone, siltstone, or shale. So that's a lot to take in on why limestone needs to be carefully described, because it can be in deeper water, but there comes a point where it's too deep for coral type material to be made, but it kind of goes all the way to about that 800-ish mark where we start getting that light that can penetrate down into the water to allow for various different biological life to thrive. So now that you've learned about these rocks, I kind of wanted to put them in perspective. So what is a marine facies? It's a series of sedimentary rocks, not igneous, not metamorphic, only sedimentary, that are, keyword, simultaneously. They're made at the same time. These rocks are simultaneously deposited during the same geologic time frame, just at different GPS coordinates. So you start with GPS coordinate number 1 at the shoreline, where you're going to see that rigorous water action I showed you at the beach in Hawaii. Then you're going to get the near shore, which is going to, so you move from sandstone, and the near shore, you're going to make siltstone. So newsflash, we don't just go from sandstone and poof, we're all of a sudden to siltstone. It grades gradually. In other words, we start with the really coarse sandstone here, and it gradually grades into a smaller grain size where we can make siltstone. Well, the same thing happens with siltstone in your near shore to your lagoon where we make shale. It's not an instantaneous, wow, we've turned into shale. It's a gradual process because you're getting calmer water, so only finer sediments can settle out. And then when you get way out here, far away from the terrigenous, this is your terrigenous input right in here along the coast, then we can start cranking out some limestone. So that's kind of how the 4 rocks form at the same time. And I wanted to give you that reference point of a beach because it really helps to understand why we can form bigger, grainier, more coarse rock there as opposed to way out here, maybe miles away from the coastline, if not tens and hundreds of miles away from the coastline before we hit wide open ocean that is thousands of feet deep. Right, that moves us into the terms for marine facies. Transgressions. Let's break apart the prefix first. Trans means to invade. Transgressions are water that invades a continent. So geologists refer to transgressions as rises in sea level. There are 3 things that primarily, and I'm going to underscore primarily, are responsible for transgressions to occur. So this picture right here is actually in Italy, and it's in very recent time. And we're looking at some sea level changes that has flooded out parts of Italy. That's not a good thing, but as climate change is continuing, sea level is rising. So be very transparent, sea level changes are documented regularly in the rock record. Unfortunately, though, for humans, we've not had these types of sea level changes that have impacted coastal habitat like they do today. So this is kind of a new thing, and it's one of the repercussions of climate change. So here are the 3 reasons that sea level rises can occur. First, you get some kind of glacial, like sea ice and or polar caps melting, which causes more water to be added to the ocean. I'm careful not to say things like the melting of glaciers maybe in Alaska. Not that that wouldn't cause some sea level rise, but when you're talking about continental ice, for example, continental glaciers and sea ice in particular, as that melts, that's definitely going to add to the amount of water that is in the ocean. Land subsidence. So I can think of a place this is happening. In New Orleans, they pump out quite a bit of groundwater for drinking water and other resources. In doing so, the land is below sea level. And as you subside it, it allows for more depth. So the land is below sea level, allowing it to be flooded. So that's problematic. So areas that were once exposed above land now become underwater. Third way, this is the one that's tricky that I want to take a minute to describe. So increase in mid-oceanic ridge development, MORs, at the bottom of the ocean. So basically it means we have diverging plate boundaries that's pushing up where they split apart, and we get these mountains on either side of them. If you're a parent, you'll relate to this because you probably want to maximize time when it comes to bathing your kiddos. Or maybe you have a dog that you need to do, or better yet, 2 of them. So I'll use dogs as an example. You've got 2 big old Labs or St. Bernards, and you're trying to give them both a bath in your bathtub. And you're putting water in the bathtub, and you put just a little too much. The dogs go in, even if they're calm about it, and just because of their volume, the amount of water in the bathtub exceeds the capacity and it spills over. So if you could imagine that spilling over on a continent, that's exactly what enhanced or more generation of active MORs causes. So in periods of time where we don't have that, the bathtub water level drops, and that would cause the opposite of a transgression. Which brings me to regressions. The prefix re means to retreat. So for every transgression, we have a regression. This refers to a drop in sea level, and when this occurs, there are 3 things, and they're just the opposite of what transgressions were. First, so maybe you get a lot of ice formation in an ice age, specifically something like sea ice or continental ice for continental glaciers being made, like in Greenland or Antarctica. Well, that's definitely going to consume ocean water. But to say that glaciers up in Alaska are going to consume ocean water, that's stretching it a bit, because it's actually formed by a process that you'll learn about later in this semester to form glacial ice. Now, part 2, if I have mountain building or uplift of the land that was submerged, now it's not. This is exactly that case in point. So what's actually happened here is that we've had a section of land that was at sea level in the last ice age, and since the last ice age, the ground has rebounded into its normal position. In some cases, literally up to 1,000 feet from where it used to be. So the prior sea level was way up here, and now it's dropped because the land has been pushed up, allowing what was once submerged to now be exposed. exposed. Remember the MOR scenario with our dogs taking a bath, right? So if you have decreased activity at mid-oceanic ridges, you're going to have less mountains and less displacement of water onto continents. MOR development, or lack thereof, is a real big driver of changes in sea level on a global scale. That brings us to understanding some of the important diagrams. So Walther's law, this is a dude that actually described transgressions and regressions, basically said this. He said, hey, when we are having multiple changes in sea level, as it's rising and as it's falling, we're going to get a vertical deposition. Likewise, we'll get a lateral deposition of sediments that stack one on top of the other, giving us a record that these sea level changes actually happened. So repetitive sea level changes create this. So you always start from the bottom. Remember the law of superposition when you're interpreting an outcrop? So this is sandstone, dash dot is siltstone. This is shale because it's all dashes. And then we get bricks, not tilted bricks, but straight up and down bricks. So this is limestone. This right here would be a perfect transgressive vertical sequence. So looking at the one right next door, you're like, well, I know that's a regression because it's the opposite. All right, could you recognize it on a test? So at the bottom, the original sea level was deep enough or far enough away from terrigenous input of sediment to form limestone, all bricks. Then it grades into shale, so it's now become a lagoon, and X marks the same GPS. So same GPS location for all four of these rock units. That means it changed its depth of water. Then above shale, I have dash dot, which is siltstone. And then the most recent of the deposition is your shoreline or your beach. So when you're looking at vertical outcrops, look from the bottom to the top and see what has sequentially been deposited. It is possible that you might be in an area, and Waco, Texas would be an example, where we have a lot of these two rocks right here. We have shale and limestone, but we're missing the sandstone and siltstone for our Cretaceous Austin chalk that you saw a minute ago when I was showing you Lover's Leap, that area right along the Brazos River. That is the running park from MCC all the way to Cameron Park. And the reason being is we were far away from a terrigenous input of sediment when there was a transgression going on. You might also remember me saying that that outcrop alternated between limestone and shale, limestone and shale, limestone and shale, and it literally makes over 20 of these sequences that you can see. So if I've got these alternating shale, limestone, that meant I went from lagoon to far away from terrigenous input to make limestone. Then when it dropped again a little bit, I could make a lagoon rock, and X marks the same spot. So if I have about 20 of these sequences, that means we had a little sea rise for limestone, a little sea drop to make lagoon stuff for shale, and it just kept alternating back and forth and back and forth. And that's how we have this remarkable rock record that we can look at. Other places you may travel to may have a dominance of the sandstone and the siltstone because they were closer to a shoreline to generate that. Right, so remember I said that you could also have lateral deposition. Walther's law also talks about the lateral deposition that happens over multiple sequences of sea level change. So a perfect transgressive sequence will have the following rocks that deposit from the bottom to the top. The bottom or oldest would be sandstone. So this is your sea level 1, your oldest here. Okay, and so you can see that we're making sandstone, siltstone, shale, and limestone all at the very same time. But notice at the bottom one, I didn't make as much limestone. But as I rise sea level to my second sea level, my beach moves further onto the continent. And you can see I'm starting to make more limestone here. Why? Because our shoreline has moved onto the continent, so there's more geographic area for me to form limestone. When I move the beach, let's say from where it is in Galveston today, maybe all the way into the middle of Kansas, So now I could be cranking out limestone all over places like Texas and Oklahoma and any state that's covered in between. So my point being is if you are looking at a transgressive sequence, the top layer, the beach is going to be furthest onto the continent and you're going to have a lot more opportunity and volume of limestone. So the opposite would be true for having a regression. A perfect regressive sequence will have the following rocks from oldest to youngest. You'll have the limestone will be biggest at the bottom because you had it further into the continent, the shoreline, right? So you generate more of it on land. And then as you lower sea level, so this is my peak sea level, and it comes down to sea level 2 and then even further on sea level 3. So it would have been like that picture I showed you after the last ice age where the shoreline drastically dropped, right? And so you can see I make very, very little limestone in my third most recent regressive sequence. So remember, transgressions are a rise in sea level, regressions are a drop in sea level. When you interpret marine facies in the field, you can sometimes see these rocks very evident. Really good place to see a perfect transgressive sequence is in the Grand Canyon. And it is right here. It's towards the gorge, not quite to the gorge. We'll get to its significance later because the Tapete sandstone down here touches Precambrian aged rock. Now, Tapete's Bright Angel, Shale, and Mob Limestone, all three of these are Cambrian in age. They start around 542-ish million years in age and progressively get younger as you get to the Mob Limestone. And down here, it's touching rocks that are literally 1.2 billion years older. So there is like, what's up with that? So if I went from a sandstone, this would be like the Hawaii beach line, then an X marks the spot in exactly the same GPS location in Arizona. We rose sea level enough to deposit a sequence of rock right on top of that sandstone known as the Bright Angel Shale. That's a famous trail, by the way, in Grand Canyon to hike rim to rim. And then you can see on top of that, we rise sea level enough that we're far away enough from terrigenous input that we can make the Mob Limestone. So you're like, where's the Siltstone? It grades between the sandstone and the shale, and then we get these really pretty, it was a fairly rapid increase in sea level. So that's why we don't have a very good Siltstone here. But this is one of the best transgressive sequences in the world to see. So when you get to historical, I promise you things are not as intense as they are in physical, and this is one of those things that you'll learn a lot about in historical. So everybody's like, I just can't take another course like this. It's so much work. It's a foundational course. It's just like taking the first biology. The second one gets a little easier. So what are cratonic sequences? When you get to historical, one of the cool things about that course is you're learning when everything happened, such as sea level rises and falls, transgressions and regressions, mountain buildings, supercontinents, when life first appeared, when it went extinct, that kind of thing. So I'm going to kind of show you how to read this, and then in historical, I'll take you into much more detail. So the craton is the interior section of our continent that is the most stable, meaning it's not bombarded by plate action like subduction zones or accretion or mountain building. If the middle sections, the craton, gets covered by an ocean, you're going to have some deposition there, hopefully. So basically, there's a dude by the name of Lawrence Sloss, and he is the one that mapped all of these out in North America. There happen to be 6 of them. So the oldest is the Sauk, that's this one down here. So the youngest is way up here called the Tejas. So what do these things mean? So let's take the section like right here. First of all, this is the west side of North America, the Cordilleran Mobile Belt. And then this is the eastern margin called the Appalachian, and these orogenies are mountain building events. So have heart, you'll learn more about that in this testing period. But nevertheless, wherever you see a lot of brown here, that represents unconformities. And the reason the middle of the continent has so much less deposition when oceans come in is because they weren't there as long, if at all. So the thinner the white section, the less rock record we have of that. So I would put maybe Arizona right in here, and that's why we have the Tapeats Sandstone, the Bright Angel Shale, the Mauve Limestone. But you can see maybe if this was Texas, for example, we wouldn't have very many rocks, if any, because this is an unconformable contact, which you're fixing to learn about. So the thicker the brown, the larger the unconformable contact. When you have lots of white here, that means we have deposition. So you can see the thickest sections of white are on both sides of the continent. Edges, meaning the margins, the coastal areas, the west coast, the east coast. And that's kind of a no-brainer because the water is going to exist there for a longer period of time, so you have more marine deposition and thicker sequences of rock. So obviously the wimpiest of all of these was the Tejas. And to be quite frank with you, we had one of the most extensive seas during the Tippecanoe. You're like, but there's a lot of white here, and you're right, there is in the Arb Soroka. But this was nationwide. It just didn't last for as long as the Arb Soroka, and that's why it's thicker. So there are 6 of these sequences. Basically, you just need to know they represent sea level changes that are documented because we can follow in that sandstone beach line and all the rocks that grade laterally, which would be the sandstone, the siltstones, the shale, and then the limestone when we're far away from terrigenous input. So the crazy thing is that we can have limestone right in the middle of the continent, right in the middle like Kansas. Even in Colorado at the tops of mountains, there is limestone which formed during these sea level events. Which brings me into a term called stratigraphy. So this is a place at the north rim of the Grand Canyon called the Coconino Overlook. And the reason it's called that is this is the Coconino Formation. It's a cross-bedded sandstone from an Aeolian environment. It's beautiful. And when we're talking about stratigraphy, it's important to marine facies and unconformities because we are looking at the extent of deposition of rock layers over a regional perspective, not just in an isolated area. So the Coconino Sandstone doesn't just exist in the Grand Canyon. You can go maybe 90 miles south to towards Sedona on the highway from Flagstaff to Sedona. The Coconino is very visible. And so the Coconino is a regional rock layer. So that stratigraphy matters, especially when we're mapping out ancient rises and falls in sea level. That brings me into talking about when rocks are conformable and when they're unconformable contacts. Conformable rock strata are those that occur in sequence without much of any kind of geologic hiatus or break. In other words, we have a pretty continuous rock record. This is shown in those rocks that I showed you earlier that are in the Grand Canyon in the beginning of the Cambrian, all the way through the Cambrian, where we see the Tapeats Sandstone from the early Cambrian, then the Bright Angel Shale comes in, and the Mauve Limestone. So these are sequentially laid down without a break. So those are conformable rock layers. Unconformable rock strata are different. They're missing time. They don't have that nice, it goes in order kind of thing. We're missing some stuff. Let's take a look at the diagram again, the photo, and show you how it changes. There's 2 unconformable contacts in this diagram. The Tapeats Sandstone's Cambrian in age, and then while Proterozoic is right beneath that on the geologic timescale, there's actually one in your section 11 chapter that I want you to get out. The difference is in how old this stuff is. So you're looking at literally about 1.6 to 1.8 billion with the B as in Bravo years old. And the Tapeats is around 542-ish million years old. So we're missing like 1.2 billion years of time in this area. It's a big gap. It's why it's called the Great Unconformity. Well, there's also missing time up here between the Mauve Limestone, which is Cambrian in age, touching the Redwall Limestone. So get out your geologic time scale and look at the amount of periods, geologically speaking, that are missing from where the Mauve ends at the Cambrian, and then the Mississippian starts. So it should go Cambrian, Ordovician, Silurian, Devonian, and then Mississippian. So we're missing Ordovician, Silurian, and Devonian in many places in the Grand Canyon. There's a handful of places that do have Devonian rocks. So this would be another big gap right here in time. So what could cause these big gaps? All right, a couple of things can happen. First and foremost, you could have a period of non-deposition where you just don't have much happening. So we don't have much probably ocean going on at the time, or the land's exposed for an extensive period of time, which will allow for the second part to occur, erosion. So you have to understand that the Grand Canyon, the bottom of it down here, used to be like a mega mountain like the Himalayas. And it's weathered down to the core of that mountain range. And this is what's that core left over. So typically when we have some kind of unconformity, we are looking at one or both of these things that could have happened. So there is a universal symbol for unconformities, just like rock layers. Now, you see a block diagram like, hey, I know those rocks. Yay, because that's important. You can see they're all the way through this, and you're like, okay, I get it now. I understand why I needed to know. You see this wavy line going on here, right? That wavy line represents an unconformity. Some block diagrams will also put them in red. That's why I put this one over here. As a matter of fact, there are multiple unconformities. This is a block diagram of the Grand Canyon, and you can see there's some towards the bottom in the gorge, and then there's some right, this big red line right here where the Deposition sandstone touches. Like in this section over here, this would be if you're going down into the gorge, you would come in contact with the Vishnu Schist and the Zoroaster granite, and then there's some of these other sedimentary rocks right here that you might have an angular unconformity, which we'll look at in a minute. My point is a wavy line, that's your signifying moment that you have an unconformity. So that brings us to the three types of unconformities, and yes, there are three major types. Now, I need you to call them by their real names. Don't call something an angular. It's an angular unconformity. So this is an obvious, this is where you have on either side of the wavy line, the unconformable contact, you'll have sedimentary rock on both sides. The difference is beneath the unconformable contact, like you see over here, you're going to have angled beds that have been tilted from their original position that were flat. They've been tilted like this, overlain by flat, younger sedimentary rocks. The missing time is right here. So the reason there's missing time is like this layer of shale and limestone and sandstone and breccia, they should be going on and on until they pinch out. But they don't. They've been wiped clean through a process of erosion. That is exactly what an angular unconformity represents. All right, there's a disconformity. So this would be like a disappearing act of rocks. How does this work? You get, here's your unconformable contact. On either side of the unconformable contact, you have flat or parallel sedimentary rocks to that unconformable wavy line, right? So these are the hardest, in my opinion, to recognize because you have to usually look at fossils, do some geology map investigations where these have already been mapped out by age and or do some testing for absolute age dating. But nevertheless, they're very common in nature. In this particular case, you're looking at the mauve limestone overlaid by the redwall limestone. All right, let's get into the nonconformities. First of all, the word non is important. It doesn't mean it's non-existent, but it is a determining factor of what type of rock is beneath the unconformable contact. In this case, you have one of two rocks that you can have. You can have igneous under there, or you can have metamorphic. In a rare circumstance, you might have both, like we do in the Grand Canyon, because this is the Vishnu Schist, and then there's intrusions of the Zoroaster granite that come beneath it. So you kind of have to know your rocks to be able to identify if this indeed is an igneous or metamorphic rock. If the metamorphic or igneous rock is at the bottom, overlain by younger flat sedimentary rocks on top, that would qualify as a nonconformity. So at the Great Unconformity, it's important to tell you that it's not just located in Arizona at the Grand Canyon. You can see it all over the world in different places, which is one reason it's so famous. In certain locations, there's only like 100 million years missing. But in this area in Colorado and most of the Colorado Plateau, indeed, the areas where the Great Unconformity is visible ranges to about 1.2 billion years. So we're going to look at the nonconformity that exists in the Grand Canyon. Now let me be clear that there's also angular unconformities and disconformities as part of the Great Unconformity within different areas of the Grand Canyon. But the most impressive age, that is the age gap, exists where we've got metamorphic and igneous rock touching flat sedimentary rock. So that's what we're going to use our testing mechanism on for this course, is the granite gorge at the bottom or the base of the Grand Canyon. So there's up to 1.2 billion years of time missing. Where did that go and what happened? So you got this igneous and metamorphic rock at the bottom, and then you get parallel flat sedimentary rocks on top. Well, the Vishnu Schist, which is a majority of what we see down here, is between 1.8 and 1.6 billion years old. And then we see right on top of it Cambrian age rocks that starts around 542-ish million years. So what happened? Fairly recent research evidence suggests that there was at least 6 to 8 vertical miles of mountain material that existed where the Great Unconformity was, like in Arizona at the Grand Canyon. And it formed as a result of an ancient supercontinent called Rodinia. So when supercontinents smash together, big mountains are formed, and as they tear apart, lots of erosion, weathering processes happen. So that's the guess right now, the hypothesis of what happened. So around 1.23 billion years ago, there was this tectonic uplift, which subsequently led to the breakup of Rodinia, which is the first supercontinent. You've learned about Pangea. Well, the first one that we have an actual rock record of happened way back when we were in the Proterozoic. So this right here is actually a nonconformity. You got igneous rock overlain by sedimentary rock right there, and that is the Great Unconformity. When you think about the Great Unconformity in the Grand Canyon, for our class, we're going to be really focusing in the Granite Gorge, and this is right here is this rock up close. So the rock is schist. Now schist is metamorphic, so you are looking at probably lavas and ashes and other sedimentary rocks that were metamorphosed and they became schist. Then later on, more recent in geologic history, around 1.4 billion years later, 200 to 400 million years later, we start getting an intrusion of granite that works its way up and gets into the actual schist. And that's an example of a Zoroaster granite vein right there. So a dike that's working its way through. And as you learned about the law of cross-cutting relationships, the granite must be younger than what it crosses over. So let's have a quick review and see what you've learned for the day. What type of marine facies is this? Is it a transgression and a regression? Which one is it and why? So remember, you need to look at the sea level. Start with the first one. This was sand. Sand moved onto the continent further, moved even further inland. Notice that the volume of limestone from my first sea level to my most recent, which is sea level 3, it's radically increased in sea level 3, which means that more limestone is being made on the continent. That must indicate that we have a sea level rise for an empiric sea to transgress onto a continent. Indeed, this is a lateral transgression. Whoops, what's this? Well, you got to start from the bottom and work your way up. We have a sandstone at the bottom, siltstone, shale, and limestone at the top. You've got it. It's just like the lateral diagram. It is a transgressive vertical sequence because limestone's at the top and sandstone's at the bottom. We're to unconformities now. So I've got sedimentary rocks up here and igneous rocks beneath them, and here's your unconformable contact. What do I have? Do I have an angular unconformity, a disconformity, or a nonconformity? And since there's igneous or metamorphic rock at the bottom, it has to be a nonconformity. All right, this is a tricky one. So here's your unconformable contact here, but you got flat sedimentary rocks on either side. So we have a disappearing act in between these flat sedimentary parallel beds. So remember, the disappearing act is indeed called a disconformity. You're looking here at the mauve limestone overlain by the red wall limestone in the Grand Canyon. What do we have here? We have sedimentary rocks that are at an angle overlain by flat sedimentary rocks. There's only one kind of unconformity it can be, and it's not an angular, it's an angular unconformity. So here we have sedimentary rocks on both sides. You got angled sedimentary rocks overlain by flat sedimentary rocks. What type of unconformity would I have? And you got it again, an angular unconformity. Okay, we've got lots of sedimentary rocks here. So this is kind of a tricky one. So I'm going to say that these have really not been tilted. Some people might say they've been tilted, but if you've been to Utah and seen these outcrops, it is the nature of the rock itself that looks this way. So it's one big fat layer of kind of a silty marl. And then on top of it, you got a flat rock on top. So you've got two sedimentary rocks with a disappearing act right in the middle. I would call that a disconformity. If indeed these are tilted rocks, this would be an angular unconformity. So you have like a pink granite at the bottom overlain by sedimentary rocks on top. I think you're getting the gist that the igneous metamorphic combo, one or the other at the bottom, automatically makes it a nonconformity. When you're looking at this, we have flat sedimentary rocks overlain by flat sedimentary rocks with a disappearing act in the middle. This would indeed be a disconformity. So let's try your hand at another. We have flat sedimentary rocks that are younger overlain by the Vishnu Schist, which is a metamorphic rock. What would you have? It is a nonconformity indeed. See your memory on this one. Well, let's just look at the diagram and see if you can figure it out, even if you can't remember what we just covered a minute ago. That was kind of why I separated them. So our first beach was far up on the continent, then it dropped, so we had a regression, and then it dropped again, we had a second regression. Now let's look at the limestone that it generated from the oldest sea level to how minimal it is on the top one, the most recent, which is an indicator that sea level continued to drop and we could no longer form limestone where it used to be. So that is, of course, a regression. So you got limestone at the bottom on this vertical outcrop, and in sequence, shale, siltstone, with sandstone being the most recent on top. Sandstone represents a regressive sequence, so this would be a vertical regressive diagram. As I conclude, I want to take a minute to talk about this remarkable place. So I had a student who was from Scotland, and he got to go back for a while, and he told me in person when he got back, he said, you know, I went here and I really was touched because I had been in geology, he had been on geology field course twice, and he also had taken my courses and knew about this place. It's called Sycar Point in Scotland. And what makes it significant is what it represents. This is where James Hutton, the father of modern geology and the rock cycle, kind of conceptualized deep time and understood that to create something like you're seeing here, which is an angular unconformity, these are sedimentary rocks that have almost been put straight up and down, overlain by newer sedimentary rocks on top. And James Hutton saw the value in this. So this is like a really famous tourist location. My point is that rocks tell stories and they contain clues that give us insight into history. So if you like history at all, if you like to kind of unravel the past and mysteries, that is what geology is all about. That's why you had to learn all the rock types. That's why you had to suffer through that, and you had to basically know the difference between an igneous, sedimentary, and metamorphic rock to get where we are now. And when you started learning about fossils, to be able to use those fossils to do some intelligent assessments of just basic age of rocks if you were to find those fossils in them. I just want to encourage you to start looking at the rocks around you with a new pair of eyes. You've been enlightened and have knowledge that most people don't. And as you start seeing rock outcrops, don't just pass them by. Stop and look at them and see what's special. See if you can decipher the clues and start to unravel the mystery of geologic time. Life is good for these dudes in Yellowstone National Park. I hope your life is as wonderful as these. Taking some time to enjoy what you see, where you are, checking out the rocks on the ground. This is what geology is all about. Have a great day. Bye.